All right, chapter 14, radioactivity and nuclear chemistry. We'll get a start on this material. We've known about radioactivity for a little bit of time. It was discovered in the late 19th century by Antoine-Henri Becquerel. The way that he discovered radioactivity, he had this hypothesis, this guess, basically just a guess, that the greenish glow of phosphorescence, think glow-in-the-dark paint, that classic green glow-in-the-dark color, was associated with the emission of X-rays like you get at the dentist's office. As you may know, if you've looked around the machine that shoots X-rays into your face at the dentist's office, they're invisible. You can't see them. So X-rays are invisible. And what he did is he exposed special crystals, potassium uranyl sulfate crystals, the uranyl part here meaning uranium. He exposed some crystals to sunlight, just like you would one of those glow-in-the-dark things if you've been to a glow-in-the-dark store, the color-changing material store. He exposed them to sunlight to get them all nice and charged up, and then he took a photographic plate, the way that photographs used to be done, put a cloth on top of the photographic plate so that the light wouldn't go through from the glow-in-the-dark paint color. And then he left it, and then took the crystals off, took the cover off. Look at this thing. It's like one of those tests where the person says, hey, what do you see here? But he saw this, and he was like, my theory is correct. X-rays have been produced and shot through the cloth material, just like they shoot through your face. So that must mean that my theory is correct. X-rays are associated with that glow-in-the-dark color, which is not true. Spoiler alert, sorry. So there was that dark spot where the crystals had been. A little bit about radioactivity. It's the emission or release, the send-off, of tiny energetic particles from some certain unstable atoms. Those unstable atoms break down. Those atoms, the ones that are unstable and break down, we call radioactive. They're sending off radioactivity, and a lot of these particles can pass through matter, at least to some extent. That's radioactivity in a nutshell. And we'll be learning about alpha particles, gamma rays, and beta particles in this chapter. But back to Becquerel. Becquerel believed his hypothesis was correct, that phosphorescence, that glow-in-the-dark color, and X-rays, the ones that go through your face to see your teeth, were linked, that both of those things happened together. Later, he discovered that even when he didn't put the crystals out in the sun so that they would glow in the dark, the dark spot on the plate still formed. So it wasn't because he was charging them up with rays from the sun and there were X-rays being released at the same time. It was actually the crystals themselves were emitting something, and it wasn't good vibes or healing energy. It was uranic rays for the uranyl sulfate, or the uranyl part of the uranyl sulfate, the crystals that he used. We don't call them uranic rays anymore. Later on, Marie Curie, famous Polish woman Marie Curie, was one of the first women in France to pursue doctoral work, going for a PhD. In her search for other substances that emitted uranic rays, she discovered two new elements. Most people have not discovered two elements in their lifetime. She did. One of them was polonium, named after her home country of Poland, and the other one was radium. Radium, which has been featured in the past on glow-in-the-dark watch hands and clocks. Used on old glow-in-the-dark watches, clocks, etc. And if I'm remembering correctly, it's not the radium that actually glows. There's another thing in there that absorbs energy from the radium, and then that is the one that does the glow-in-the-dark thing. But the cool thing about the old style of glow-in-the-dark is that it would give you cancer. Sorry, the cool part about it was that you didn't have to charge it up. It just always glowed in the dark. So you could leave it in a dark room and it was always glowing. And Curie is the one that's responsible for renaming uranic rays to radioactivity. Which one's cooler? Hard to say. But radioactivity is what we have now, and that's an important change. The 1903 Nobel Prize in Physics, Nobel Prize, a big award in sciences and other things, went to Becquerel and the Curies, Pierre, her husband, and Marie, for their discovery of radioactivity. So together, the three of them shared this award that's somewhat common, or it's at least not unheard of. And then in 1911, Marie Curie was awarded the Nobel Prize in Chemistry for the discovery of polonium and radium, the two elements she discovered, which makes her the only person to receive 2 Nobel Prizes in different science fields. There have been other people that have won 2 in the same field. She's the only one, as far as I could find, to receive 2 Nobel Prizes in different science fields. And this is a picture, I believe this is all 3 of them, Marie, Pierre, and Antoine Henri, or Becquerel. So that's a little bit of the history. I think the history is not something that I'll probably test you on, but it's good to know. I think it's kind of fun. Curie focused her work on discovering different radioactive elements. I would say she was quite successful. And others, like Ernest Rutherford, focused on characterizing radioactivity. How does it work, basically? Why did I skip the O? How does it work? That's the characterizing part. Figuring out exactly how we can use it, how it works, what it does, all those sorts of things. It turns out the nuclei being plural of nucleus, a nucleus being where our protons and our neutrons are in an atom. The nuclei of radioactive elements are unstable and spontaneously decompose. They will do this by themselves without outside intervention or action. So if you leave an unstable nucleus by itself, it will just randomly decompose. And for the most part, there's not really anything you can do to help that along. So they just kind of fall apart for reasons beyond the scope of the class. We've got 4 types of radioactive emissions that we'll talk about. Alpha, there's the symbol alpha. We've also got beta, the symbol beta following it, and gamma, and then also positrons, which don't have a cool symbol for them. Questions so far? To preempt, yes, you will have to know each of these 4 types of radioactivity. Before we get to those, let's review our nuclear symbols. We've looked at these before. So our nuclear symbols, we've got X, which is our chemical symbol. 1 or 2 letters. The first letter is always capitalized. These are what we would find on the periodic table. And then we've got 2 numbers. We've got a mass number. The mass number is protons plus neutrons. The reason that the symbol is A is because of the Germans. It's like Atomgewichte or something like that. Atomic weight is why it's A. Thank you, Germans. And then we also have the atomic number, which is just the number of protons. And the reason that it's the letter Z because of the Germans, again. Z for Zahl, which is number, or however you pronounce it. Sorry, Germans. So our mass number, number of protons and neutrons, atomic number, the number of protons. And these two are linked, the atomic number and the chemical symbol, because the atomic number determines the element, determines the chemical symbol. So those two go together. So if you have one, you can figure out the other one. If we want to figure out the mass number, it's, again, protons and neutrons. You can also figure out the atomic number by doing a little bit of relatively simple maths. Most elements have several different isotopes. An isotope is the same protons, same number of protons, so it's the same element, but different neutrons, different number of neutrons. So there's a couple of configurations, just like cars have a couple of different configurations. You can buy them in different trim packages. They come in different colors. Atoms, sort of a similar thing. You can have different numbers of protons in there, or different numbers of neutrons, sorry. Protons is the one that doesn't change. And we often refer to a particular isotope, so one isotope of an element, as a nuclide. So nuclide just means one isotope, not talking about the element as a whole, the whole collection of possible numbers of neutrons, but just one of them. And another way that we can represent the isotopes is by taking the element name or symbol and putting the mass number after it. So carbon has a couple of different nuclides. One of them is carbon-12. That's the stable carbon. So you can represent it as carbon dash hyphen on dash, whatever it is, 12, or C12. There's also C13 and C14 that exist. C12 is the most common one. That's why our molar mass for carbon is closer to 12. We can also represent our main subatomic particles, so that the particles that make up our atoms can be represented with these nuclear symbols. A proton is 1 over 1p. This top 1 meaning there's one proton and neutron combined. It's just a proton, so it's just one proton. The bottom number being a 1 because it's one proton. And then the symbol P for proton. For our neutron, we have 1 over 0 n. N for neutron, a 1 up top because we've got one neutron. A 0 down below because we have 0 protons. And the electron, getting the symbol E, and this one's weird because it's got a negative 1 in the Z spot. I just think of that as it's a negative charge. So negative 1 charge. And the 0 up top, because it's neither a proton nor a neutron, it's just a small little electron. And we'll start alpha decay, talking about alpha decay next week.